Good morning. We seem to have survived until the last day of class. So congratulations to all of us. What I want to do today is mostly review. I want to review what we've done in chapter 12 and do a couple more things. And then I thought I'd work with you a problem that reviewed some other key concepts in the course. So that's the agenda for today. So let's begin. So we have been talking about randomness at the microscopic level. And we've been using our ball spring model of the solid to think about randomness in terms of distribution of energy among lots of atoms and bonds that are vibrating in the solid. We've been using for this the simplified model of a solid proposed by Albert Einstein, which is called the Einstein Model, and it's a modification of the ball spring model of a solid in which each atom is modeled as three independent quantum oscillators. So an atom in our 3D model of a solid has bonds in the X, Y, and Z directions. And so it can oscillate in X, Y, or Z. And our model simplifies it to three independent oscillators that don't affect each other and don't affect neighboring atoms, corresponding to these three, what are called degrees of freedom, basically. So oscillations in X, Y, and Z. Because this is a tiny system, it has the property that the energy of the vibrations is actually quantized. Energy meaning kinetic plus potential energy. So kinetic energy and spring potential energy. And the difference in energy between two adjacent energy levels is this quantity h bar omega 0, where omega is here the square root of the interatomic spring stiffness divided by the mass of an atom. And h bar is Planck's constant over 2 pi, so it's 1.05 times 10 to the minus 34 joules seconds. We came up with a formula, a probabilistic formula for the number of ways of arranging some number of these little energy packets, these quanta of energy, which has a value in joules, of course, for any particular substance, among n of these independent oscillators, where the number of ways of arranging energy was q plus n minus 1 factorial over q factorial times n minus 1 factorial. And in VPython, remember that can be calculated as combin of q plus n minus 1 and q. And we defined the terms macro state is the system plus the total amount of energy, and a microstate is one particular arrangement of energy. And every microstate, the fundamental assumption of statistical mechanics is that every microstate, each arrangement, is equally probable. Last time we looked at a question or gave you sort of graphical pictures of ways of arranging of some particular microstates and asked which was the most probable. You remember, let's see, this question. And the thing to note is that, first of all, it turned out they're all these arrangements are equally probable because each one is just one way of arranging energy. The thing to think about is that each of these things is actually incredibly improbable because there are so many, many, many different ways of arranging 25 quanta of energy among 100 oscillators that the probability that if you took a photo of this system that you'd find any of these is actually very small. So probability. And we found that entropy, which was a concept that was first invented long before people knew about the atomic composition of matter, entropy turns out to be related directly to the number of ways of arranging however much energy you've got and however many oscillators you've got. And that entropy is the Boltzmann constant K sub B times the log of the number of ways of arranging energy. So there's a question of how you do natural log in VPython. So in Python, as in many programming languages, the natural log is just log of x. If you want log base 10, then you actually have to say log 10 of x in VPython. So log is actually the natural log in VPython and in many other programming languages. We also saw that we could think about equilibrium, in which we put two different objects in contact and just wait, that the most probable distribution of energy was the one that corresponded to the most microstates. The macro state that is most probable is the one with the most microstates. And we would see that most of the time if we sampled over time. We also saw that for a combined system with two objects in contact, the total number of ways of arranging the energy was the product of the ways of arranging, really, the number of microstates for object 1 and the number of microstates for object 2. Because for every microstate in object 1, you could have all the different microstates in object 2. And this leads to the mathematical consequence that the total entropy of the system is just the sum of the entropy of object 1 and object 2 because of this log relationship. So the log of omega 1, omega 2 is log of omega 1 plus log of omega 2. So total entropy is just the addition. We also talked about the laws of thermodynamics. The first law of thermodynamics, as we know very well, because it's just the energy principle, which we've been talking about for a long time. So the energy of a system can change only by inputs from the surroundings. It could be work, it could be transfer of energy, thermal energy due to a temperature difference, it could be radiation coming in. So, and we have different ways of stating it. We can state it that way. We can state it as the change of energy of the system plus the change of energy of surroundings equals 0. So energy never gets lost. What's new is the second law of thermodynamics, which really at its root is based on this whole probabilistic view of what's happening at the microscopic level. And there are lots of ways of saying it. One way of saying it is that if a closed system is not in equilibrium, the most probable consequence is that the entropy of the system will increase. And what's a closed system? Well, it's isolated from its surroundings, so no inputs from its surroundings. So of course, the universe is a closed system because it doesn't have any surroundings. So you may hear people say the second law of thermodynamics says that the most probable thing is that the entropy of the universe will increase. So there are lots of different ways of saying it. We also talked about two objects in thermal contact. For example, large block and a small block, maybe with 400 oscillators in one, 100 in the other, and total number of 100 quanta to distribute. And we discovered that if we plotted the entropy of object 1, object 2, and their sum versus the amount of energy in object 1, we got graphs that look like this, where the entropy of object 1, of course, increases as more energy gets put into object 1, because there are more ways to arrange more energy. The entropy of object 2 decreases as more energy goes into object 1, because there's less energy to arrange. But the total entropy, the sum of these two things, ends up having a maximum at the most probable equilibrium distribution, which it corresponds to the largest possible number of microstates. And since we knew that, so the equilibrium, the expected distribution of energy at equilibrium is given by this point at which is the total entropy is a maximum. And from noting that, we were actually able to deduce that since it's a maximum, dsde is 0 there. And from that, we were able to deduce that the definition of temperature is that 1 over the temperature is the rate of change of the entropy of a system. So I have a question for you about this, a graph like this one. And it's this. We saw that the maximum, the situation with maximum entropy is the situation that's most probable equilibrium. What is the meaning of the location where the two black lines cross? So the two lines, S1 versus energy and S2 versus energy in block 1, cross at that line. What is the meaning of this crossing point? So the majority said that that indicates the most probable, oops, typo, should be most probable, not most probably, energy distribution. But that can't be right. So let's look at this a little more carefully here. The point with, so we just got finished saying here that the point where the entropy is a maximum, that corresponds to the situation with the most possible microstates corresponding to it. So this, the energy corresponding to when entropy is a maximum, that's the equilibrium energy distribution. And so that is the most probable energy distribution, because that's what you're going to see at equilibrium. And the bigger the objects are, the more sharp that peak actually is. So that's not the most probable energy distribution. This point where S total is a maximum is the most probable energy distribution, and that is the same thing. That's where the entropy is maximum. Now the minimum entropy looks like it's here, and that's not it. So it's not the minimum entropy. So unfortunately, it turns out that this point, which your eye really wants to look at on this graph, actually doesn't mean anything. So the 5 people who said that are correct. There's actually no particular meaning to this value of S or that value of Q. It's just where these graphs cross. So don't get tricked by these graphs. You have to think about how to interpret them. Let me remind you about a practice quiz that's available on this topic. Okay. So I want to actually just calculate a couple of entropy changes with you in a particular situation. So we know that 1 over temperature is equal to, or it's equal to dsDE, so it's approximately equal to delta S over the change in E, where this is E is internal energy, right? So we could write this as the change in entropy over Q, the transfer of energy due to a temperature difference, if work is 0, no work is done on the system. So does the intersection indicate that the objects have the same amount of internal energy? Yes, right? Because, well, no, it doesn't. Because it doesn't indicate that either, because Q in this graph here, for example, which was, I think, for a system that had, I think it was this thing with 400 and 100 oscillators. So we had for them to have equal amounts of internal energy above the ground state, then Q1 would have to be equal to half of the total possible, right? So it would be maybe sort of here where Q1 equals Q2. So it doesn't even mean that. It doesn't really have any information in it that we could use. It's just something our eye really wants to look at because it's an interesting point visually. So this relationship, temperature is dsDE, and if there's no work done, that's delta S over Q, the amount of energy transferred due to a temperature difference, could lead to a relationship that the change in entropy of a system is equal to Q over the temperature, provided if the process happens at a constant temperature. So if the temperature doesn't change, even though there's energy, thermal energy flowing, the temperature doesn't change. Well, there is a process like that, and you may have actually done experiments with this in a chemistry class or a physics class before, and it has to do with melting and freezing. Which actually occurs at constant temperature. So if you, say, melt a solid substance, so this is the temperature versus time, and what you're doing is you're taking something, a solid piece of metal or an organic crystal or an ice cube or whatever, melting it, you'll find that the temperature of this object, as you put in energy into it, so you're heating it, the temperature goes up until it gets to the melting point. And then the temperature is constant as the thing melts, and then it starts to go up again once it's a liquid, and so Here it's melting or freezing if you're going the other way. So it's sort of an interesting thing to look at entropy changes in this process, because we can ask questions like, can entropy ever decrease? And if so, for what? For the system? For the surroundings? For the universe? So it's sort of interesting just to do a simple calculation to analyze this. So let's melt ice. So 1 gram of ice requires 335 joules to melt. And the temperature is constant at 0 Celsius, well, or 273 Kelvin while it's melting. So what we're going to do here is we're going to take a gram of ice and we're going to put it on top of a room temperature metal so it's at 293 Kelvin. And we're going to calculate the change of entropy of the ice, the change of entropy of the metal, and the change of entropy of the universe in this situation. And in this process, the temperature of both of these things is constant. The temperature of the ice is constant because it's melting. The temperature of the metal is essentially constant because it's a big hunk of metal, and a little teeny bit of energy flowing out doesn't actually change its temperature very much. So we can calculate the change in the entropy of the ice. So we have to put in 335 joules, and the temperature is of the ice / water remains at 273 Kelvin. And so that comes out to a plus 1.23 joules per Kelvin during this melting process. The change of entropy of the surroundings, that's going to be the block of metal here. Well, energy flows out of the metal to the ice. So we have a minus 335 joules, and this thing stays at 293 Kelvin. And so that turns out to be a minus 1.14 joules per Kelvin. And so the change of entropy of the universe, which is the change in entropy of the ice plus the change in entropy of the surroundings, is a plus 0.09 joules per Kelvin. So entropy of the universe, and let me remind you that we're using this relationship here where we had 1 over T is delta S over Q, so change in entropy was Q over T if T was constant. Okay, so when we melted ice, the entropy of the universe, of the surroundings, actually decreased. The entropy of the ice increased, and it increased more than the entropy of the surroundings decreased, so the total change in the entropy of system plus surroundings was a positive number. So the entropy of the universe increased. Okay, well, let's see what happens, and then we go the other direction. So we're gonna freeze water. So we have a little puddle of water, a gram of water. It's at 273 Kelvin. And we have a metal here. It's colder now, so this thing can freeze. So it's at 253 Kelvin. So we freeze water. So we're just going to do the same calculations. So we can calculate the change in entropy of the water. Well, it requires an input of 335 joules to melt a gram of ice. So we have to take 335 joules out to freeze a gram of water. So the change in entropy of the water is negative 335 joules divided by the temperature, 273 K. So that's a negative 1.23 joules per Kelvin. So the entropy of the water in this case actually decreased. Now the change in entropy of the surroundings is going to be, well, the metal block absorbed the energy that was lost from the ice. So energy flowed from the water as it turned to ice. So energy flowed from the water into the block. So the block gained 335 joules of energy, and it stayed at a temperature of 253 Kelvin. And so its entropy increased by an amount of 1.32 joules per Kelvin. So this time, the entropy of the water decreased, but the entropy of the surroundings increased. And so the total change of entropy of the system plus surroundings, let's call it water here, plus the change in entropy of the surroundings is going to be plus 0.9 joules per Kelvin. So the entropy of the universe increased again. So in all these processes, the entropy of the universe is actually increasing. Okay, let's see if we can answer a question. So here's our question. We have two objects, and initially they have exactly the same entropy, which is 100 joules per Kelvin. And then each object is put into a really, 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 really big vat of hot water. And we find that for object A, when its thermal energy is increased by 100 joules, its entropy is now 200 joules per Kelvin. And when the thermal energy of B is increased by 2000 joules, its entropy is 300 joules per Kelvin. So the question is, which object is at a higher temperature? So you probably need to do just a little arithmetic. Okay, so most of you think that 47% think that B is at a higher temperature than A, but 29% think that temperatures are the same, and 24% think that A is higher than B. So there's some confusion here. So this is just a case where you have to apply a definition. So remember that 1 over temperature is ds dE, so that 1 over temperature, this is going to be approximately delta S over delta E, change in entropy over change in energy. So temperature is approximately change in energy over change in entropy, right? So let's just calculate these. A, we have T sub A is going to be the change in entropy, which is, and we need two values for a change in entropy. So that's 200 joules per Kelvin minus 100, whoops, that's in the numerator, 200 joules per Kelvin minus 100 joule per Kelvin. And the temperature went from 2000 Kelvin to, the energy went from 2000 joules to 1000 joules to 2000 joules. So it looks like we have 1000 over 100, which is going to be equal to 10 Kelvin. For B, we need two values of temperature, of energy, sorry. So we have oh, sorry, it's just an, let's try that again. Read the problem. Energy has increased by 1000 joules. So we have 1000 joules increase in energy, and we have 200 joules per Kelvin minus 100 joule per Kelvin. So that's 1000 over 100, which is 10. Here the energy is increased by 2000 joules, and the entropy has gone from 300 to 300 joules per Kelvin, but it started at 100 joules per Kelvin. So we have 2000 joules over 200 joules per Kelvin, and we get 10. So actually, their temperatures are exactly the same. And I think the takeaway lesson here is that to get temperature, you need two values of things. So you need 1 over temperatures, you need S2 minus S1 over E2 minus E1. Okay, it's a change. And so it's not the amount, it's the slope of the line, right? It's not amounts, it's slopes. This thing that plagues us always. We keep wanting to use amounts instead of slopes. So as those people who came to recitation on Tuesday found, to calculate the temperature of something, so for temperature, you need a change in energy, and you need a change in entropy. So for example, if we started off, we said here we have a block of metal with 150 oscillators, and the energy of one quantum was 4 times 10 to the minus 21 joules. Calculate its temperature when it's got 11 quanta. Well, what we'd have to do is we'd have to actually have two values of Q, so we could get two values of omega at 10 and omega at 11, so we could have two values of entropy, S10, S11, and so we could get a delta S. And so we could use that to T is approximately delta E over delta S. Now we could actually go a little further in this calculation. We could actually, if we had, we know that heat capacity is, or specific heat, is the amount of energy per Kelvin. So heat capacity for an object, energy per Kelvin, specific heat, heat per Kelvin per something, per gram or per atom or whatnot. So if we had one more value of ways of arranging quanta and one more value of entropy, we could get another value of delta S. We could get two temperatures. And now we could use these to get a delta T, which would actually let us predict specific heat. Now, why is this interesting? This is actually interesting because until the beginning of the 20th century, people thought that specific heat was just a constant value. But when it became possible to cool objects down to closer and closer to absolute zero, people discovered that specific heat was not constant. And in fact, it looked something like this. When people made measurements of, were able to measure specific heat, this is on a per atom basis for solids, at low temperatures that were lower than room temperature. So down here, below 300 Kelvin, getting close down to, can't quite get to absolute zero, but close. They found that it went down hugely as the temperature went down. Now we would think of this as went down as the energy content goes down, and that's related to temperature because it's related to entropy. Well, if we, and so these are data actually for the literature, measurements of specific heat on a per atom basis. The red ones are for aluminum, and the blue ones are for lead. And you can see that as it gets, the temperature gets close to room temperature, these things approach the same value. They're not exactly the same value, but they approach the same value. So if we just tell VPython to do these calculations, and first we have to calculate the amount of energy in one quantum for aluminum and lead, which we can do knowing the interatomic spring stiffness. We can predict the temperature as we start putting more and more energy into these things. We can just do the calculation that we just outlined. And when we do that prediction, here's what we get for aluminum. We find that our prediction, and when we use the interatomic spring stiffness we got by stretching aluminum wires and calculating Young's modulus and finding the interatomic spring stiffness, our prediction is very close to the observed values. And likewise, when we put in the values for lead, which is a much softer bond and a much more massive atom, we find that our prediction is really very close to those values too. So it turns out that from what we did in chapter 4, just hanging weights on a wire and stretching it, we were able to learn enough about the nature of the interatomic bonds in solids, and from our ball spring model in solids, we're actually able to predict something fairly sophisticated, which is the variation of specific heat with temperature for different substances. Yes, the specific heat obviously decreases a lot here as the temperature gets close to absolute zero. And you can think of it that means that the specific heat is change in energy over change in temperature, right? So the change in energy over the change in temperature becomes smaller as we get to smaller and smaller temperatures. And we're calculating temperature based on changes in entropy as a function of energy. So basically, this is second differences here. I wouldn't think of it as warming up the springs. I mean, I think the way I think of it just goes back to the basic model we've been talking about, where when you only have a tiny amount of energy, there aren't very many ways of arranging it. So the entropy can't change very much, even when you put in more energy. When you end up with a lot of energy, there are a lot of ways of arranging it. And so you can get a big change in entropy as you put in energy. So it comes back to this ways of arranging energy idea, basically. I thought it might be a good idea to actually look at a completely different problem, just kind of as a review of lots of the other stuff that we've done in this class. So now for something completely different. Let's think about the following situation. So we have a bullet. This is in outer space, so no external forces. We have a bullet heading at fairly high speed here. So at a sort of a dumbbell shaped object that's just floating in space. So we're in outer space here. Initially, this dumbbell shaped thing is at rest. The bullet comes in and actually embeds itself. These masses are wood, so it embeds itself. Bullet embeds itself in this object. And you can just think for a minute about what's going to happen here. So we want to find out three things. We want to find out the velocity of the center of mass of this object after the impact. We want to find the angular speed after impact. And we want to find out the increase in internal energy of the device after impact. And by the device, we now mean the device including the bullet. Okay. So what fundamental principle do we want to use to start from to find the velocity of the center of mass of the object? Momentum principle, that sounds like a good idea. So momentum principle. What fundamental principle do we want to use to find the angular speed of the object after the impact? Yeah, angular momentum principle. And this leaves energy calculations to get the final. Now notice that we can't, we have to, I mean, so we're using some sort of heuristics to decide what principle to use. The momentum principle involves vectors, and we want a vector velocity. And so energy isn't going to help us here. We can't use the energy principle to find the angular speed either, because we can't assume this collision is elastic. In fact, we know it's not elastic because the bullet sticks into it, and so that's really, really, really inelastic. So we know for sure it's not elastic. So we actually need to. So we're going to touch on all three fundamental principles in solving this problem. So let's make this just a little bit smaller so we have a little more room to write here. Okay. So A, we want the momentum principle. So we say the final momentum of the system is equal to the initial momentum plus F net delta T. And what are we going to choose as our system here? Yeah, that's right. We want to choose everything, because we're not going to be able to separate the bullet from the rest of the system afterwards. So the final momentum, well, the bullet's stuck into the dumbbell here, so we want the mass of the bullet plus the mass of the dumbbell. So I'm going to say mass of the dumbbell is 2 times 1.6 kilograms, and that's mass of the bullet, times the final velocity is equal to the initial momentum. Well, initially the dumbbell's at rest, so we just have the mass of the bullet times the initial velocity of the bullet. And because this is a collision, and we're looking at the process from before to right after, we can say that external forces due to objects not in our system are negligible. So in fact, we just have a 0 here. And so we can actually just get the final velocity as the initial momentum divided by the mass of the combined objects. So that's 0.003 kilograms times 0 minus 400 meters per second divided by 2 times 1.6 kilograms plus 0.003 kilograms. And that's going to give us, if we work it out, 0 minus 0.3750 kilometers per second. So we go back and think about it. This means that what happened to this thing is when the bullet hits, it starts to rotate, of course, which we haven't accounted for yet. But it also now has momentum equal to the momentum of the bullet before it hit this thing. So it's not only rotating, it's also moving apparently fairly slowly in the minus y direction. So kind of a complicated motion. And of course, if we were asked, where would this thing be 3 seconds later? So we could say, we could use our final as our initial plus v final delta t to update its position. Okay, so that was part A. Part B is the angular speed. And now we really do need the angular momentum principle. So let's think about angular momentum. Let's just think qualitatively for a minute. First of all, we want angular momentum about some location, right? So what location are we gonna choose to calculate angular momentum around? Well, the center of mass of what? Well, the center of the dumbbell is definitely the location I would choose for this, but it isn't going to end up being the center of mass of the final system, actually. It's the center of mass of the dumbbell before the bullet hits, but once the bullet embeds itself in this block, the center of mass is actually going to shift just a teeny bit to the left, right? Now, 0.003 kilograms, so 3 grams is not going to be a big deal compared to 1.6 kilograms, so it won't shift very much. But, so, just a tiny bit. Okay, so we're going to pick the center of the dumbbell. So we're going to want the angular momentum principle, which tells us that L final is L initial plus the net torque around location A delta T. And fortunately, this is a collision and we're in outer space, so there isn't anything interacting with this thing anyway. And so in fact, that's going to be 0. And what are we choosing as our system? So we have 3 choices. We could choose the bullet as a system, we could choose the dumbbell as a system, or we could choose. So we could choose, it's completely legal to choose just the dumbbell. However, if we choose just the dumbbell, then in fact there is a torque on the system. So if we choose the dumbbell, then the net torque is not 0 because the well, it's not a crazy idea. It's doable this way because the bullet hitting the dumbbell hits the end and delivers an impulse. So the bullet now exerts a torque. And so we'd need to know the force. We actually can figure out the force. It's a little complicated because the change in momentum of the bullet should be equal and opposite. The change in momentum of the bullet tells us the impulse applied to the bullet, right? And so an equal and opposite force should be applied to the dumbbell. So we actually could do it that way. We need to know P final of the bullet, which is, we know the velocity of the center of mass, so that's almost P final of the bullet, but it isn't quite because this thing is spinning, so we need to know that also. So it would work to do it that way. And you can actually work this out this way. A different approach So torque, so that's okay. It's a completely legitimate approach. If we choose the system as both objects, then we're going to have the final angular momentum is equal to the initial angular momentum plus the net torque due to things outside the system, and now that's zero. So that's a different way to do it that I think is slightly simpler, but you may not think it's simpler, and it's possible to do it both ways actually. So let's see what happens when we do it this way. So the final angular momentum kind of has two pieces. It's got the angular momentum of the dumbbell and the angular momentum of the bullet embedded in the dumbbell. And initially the dumbbell is not rotating, so the only thing we have is the initial angular momentum of the bullet. So let's see what the initial angular momentum of the bullet's going to be. So this is going to be translational angular momentum, and we want to take the bullet right before it hits right as it contacts the dumbbell, and then we have an R sub A here that's pretty much just in the x direction. And so we can expand this as R sub A cross mass of the bullet times the initial velocity of the bullet. So that's the initial angular momentum of the bullet. Now the final angular momentum of the dumbbell is going to be the moment of inertia of the dumbbell times its angular velocity, right? In the bullet here, we can think of we can't, so the bullet is actually traveling tangentially here. And so it's got translational angular momentum. So it's RA cross M bullet V bullet final. And the thing we're trying to find here is this omega final. And so we know all this stuff, that's fine. We can calculate the moment of inertia of the dumbbell. We know R sub A, which hasn't changed. We know the mass of the bullet, but we've got this other unknown, and that's a problem. So we're going to have to express this quantity. We want to express this in terms of omega final so that we can have only one unknown here. Before we do this, though, let's see if we can actually take only one component. So let's look at directions. So the translational, if we use the usual coordinate system here where we've got x, y, and z coming directly out at us, what's the direction of the translational angular momentum of the bullet just before it hits the dumbbell? So we have here's the bullet, here's the momentum of the bullet, here's R. Oh, I actually drew RA backwards, didn't I? You guys should have caught that. R goes from A, okay. Okay, so it's R cross P. So it's this we're looking at here, this quantity here. And so if we put these vectors tail to tail, we have R sub A, we have P, we use our right hand. So we do indeed get plus Z. And if you had trouble with directions of angular momentum on the last test, this is something you need to review. Okay, so that's in the plus Z direction. What is the direction of the angular momentum of the dumbbell once it's rotating? So all we need to do is we just curl our fingers around in the direction the dumbbell is rotating. Our thumbstick, yeah, plus Z, that's right. And the bullet is traveling with the same sense as the dumbbell, so its angular momentum is also plus Z. So everything's plus Z, and so we can actually just, we know that the direction is going to be plus Z. We can just do magnitudes now. So if we have in the plus Z direction, we have the moment of inertia of the dumbbell, which is 2 times 1.6 kilograms times the distance to the center squared, so 0.05 meters times omega final. And remember, we can express the speed of the bullet, which is now going around with the, as it's equal to omega final times R, which is R sub A. So this whole thing turns into R sub A times the mass of the bullet times omega final R sub A times sine of 90 degrees. And that's equal to R sub A mass of the bullet, the initial speed of the bullet, sine of 90 degrees. And now we're in good shape because we've only got one unknown. So we can solve for omega final. Which comes out to be, let's see, RA mass of the bullet, the initial speed of the bullet divided by RA squared times the mass of the bullet plus the moment of inertia of the dumbbell. And when we plug in all those numbers, we're going to get omega 0.749 radians per second in the plus Z direction. Now, it would have actually worked to do it Seth's way, where we actually calculate the torque. I mean, that's perfectly fine. We need to calculate the change in the bullet's momentum to get the force, but we can do that. So finally, this thing should have gotten hotter. because the bullet embedded itself in the dumbbell. So the final kinetic energy plus the final internal energy is the initial kinetic energy plus the initial internal energy plus any work done by on outside external forces plus transfer from the surroundings due to a temperature difference, and these are both 0. And so the change in internal energy is just going to be the initial kinetic energy minus the final kinetic energy. And the initial kinetic energy, that's easy. It's just a half times the mass of the bullet, speed squared. The final kinetic energy is a little awkward because it's got two pieces. We have this translational kinetic energy due to the whole thing moving. So it's a half times the total mass of the system v squared. So this is k trans. And then we have the rotational kinetic energy of the dumbbell, which is just half I omega final squared. And then we have basically the rotational kinetic energy of the bullet, which is a half times the mass of the bullet times its speed squared, which is RA omega final squared. And if we work these things out, this comes out to an initial kinetic energy of 240 joules. And this is the translational kinetic energy is not very big, 225 joules. And it turns out that this is also 0.225 joules. And this number is really tiny. It's like 2 × 10⁻⁴ joules just for the bullet. And so we get something like 239.5 joules. So most of the energy of the bullet actually went into internal energy of the system. Yeah, that's right. That problem took us the whole semester to explain, didn't it? That's right. So that was a review of pretty much the whole semester, except for chapter 12.